Welcome back to the Deep Dive. Today we're embarking on a journey into the pretty surprising world of light. We're going to explore optical phenomena, those incredible ways light interacts with its environment. It leads to some of nature's most stunning visual displays and, well, some truly ingenious technologies that shape our everyday lives. For this deep dive, we've pulled insights from a specific section of a physics textbook, Chapter 15, Section 3, all about optical phenomena. We've got your notes in this material right here, packed with really fascinating details.
Yeah, and our mission today is really to distill those key concepts for you. We want to turn what might look like complex physics into clear, memorable insights. We'll explore everything from how light can get totally trapped, which is amazing, to why the sky sometimes, plays tricks on our eyes, and even the secret behind a rainbow's vivid colors. Our goal is to give you a shortcut to being truly well-informed about these often overlooked wonders.
Okay, let's unpack this. And where better to start than with something kind of counterintuitive? Total internal reflection. It sounds like light is just bouncing around, maybe. But there's a fascinating catch. So what exactly is this phenomenon, and what unique conditions make it happen?
Right. What's fascinating here is that total internal reflection, or TIR, isn't just any bounce. It's the complete reflection of light. It happens when it tries to cross a boundary between two transparent materials. But the crucial condition, the real key, is that light must be moving from a medium where it travels slower to one where it would travel faster. Think of it as light moving from, say, water into air. That's the classic example. Or, to put that another way, we talk about the index of refraction.
Yes, index of refraction.
Yeah, think of the index of refraction as like a measure of how much a material bends or slows down light. The higher the index, the more light slows down. So for TIR, light needs to move from a material with a higher index of refraction to one with a lower index of refraction. Figure 1512A in your materials kind of shows how some light might normally refract out, but other rays behave quite differently.
Okay, so it's not just any light ray going from water to air that does this, right? There's got to be a tipping point. Yeah, like a specific angle where the light just decides, nope, I'm staying put. Is that what we call the critical angle?
Precisely, you got it. The critical angle is that, well, magical minimum angle of incidence where total internal reflection actually begins. At this specific angle, the refracted light ray literally skims parallel to the boundary. It makes its angle of refraction a full 90 degrees. You can see this really vividly illustrated in figure 1512b. And here's the thing. For any angle of incidence greater than that critical angle, the light ray is entirely reflected back.
Wow, entirely.
Entirely reflected back into the denser medium. It's like the boundary becomes the perfect mirror, basically. And the law of reflection angle of incidence equals angle of reflection. It applies perfectly here.
That's fascinating. So it's less like a traditional mirror and more like the light just hits an invisible wall it can't get through. But the real-world application here is incredible. Our sources mention how prisms, like the ones you might find in binoculars or periscopes, they're often used instead of traditional mirrors for this very reason. Why is that? Why are they a better choice?
Well, a couple of reasons. Prisms reflect light far more efficiently than, say, metallic mirrors. Plus, they're much more durable, more scratch-resistant too. Like, take a periscope. It often uses two 90-degree prisms aligned just right, side by side, to let you see above or around corners. What's truly profound here is that we can predict exactly when this no-escape condition happens. A fundamental principle called Snell's law, it tells us that total internal reflection only happens when light moves from a denser to a less dense medium. The math just wouldn't work, otherwise it wouldn't allow for a real angle. It basically guarantees light gets trapped inside under those conditions.
So, okay, let's bring this home. What does this all mean for something, dazzling? Something you might see every day or wish you could? Let's talk about diamonds. They have an astonishingly high index of refraction, right? Around 2.419. How does this super high index make them sparkle like nothing else?
Yeah, that high index of refraction is key. It gives diamonds a remarkably small critical angle, just 24.4 degrees, tiny. And what's truly profound here, I think, is how we've taken this fundamental physics principle TIR and, through really meticulous craftsmanship, transformed a simple mineral into, a symbol of ultimate brilliance. Because diamonds have such a tiny critical angle, most of the light that enters a carefully cut diamond, it gets totally internally reflected, again and again.
So it bounces around inside.
Exactly. Jewelers cut them specifically to maximize this internal dance of light, making it exit from the most visible faces, the top facets usually. That's what gives a diamond its incredible fiery sparkle. It's very different from, say, crown glass, which has a larger critical angle, about 41 degrees, and much less fire.
That's a perfect example of physics meeting art. and maybe commerce too. But this concept isn't just about pretty rocks, is it? How do we actually get light to travel around corners? This brings us to fiber optics.
Fiber optic cables are a direct, really clever application of this principle. They're essentially transparent glass or plastic rods, often incredibly thin fibers bundled together. And the magic is that light is sort of confined to travel within these rods or fibers. It can even go around gentle curve because of successive internal reflections.
Oh no, so it keeps bouncing.
Yeah, each time the light ray hits the inner surface of the fiber, if its angle is greater than the critical angle, it just bounces right back in. It continues its journey down the fiber. Figure 1513 in your notes shows this beautifully, that zigzag path.
Okay, so this invisible dance of light trapped inside these like hair-thin glass strands.
Yeah.
What are the practical implications? It sounds incredibly useful.
Oh, it's revolutionary. Seriously. Fiber optic devices are incredibly practical for viewing images in places you just can't normally see. Think about it. A tiny fiber optic cable threaded down the esophagus into the stomach to look for ulcers. It allows doctors to literally see inside the human body without major surgery. And if we connect this to the bigger picture, fiber optics are basically the fundamental engine powering our interconnected world today. They're increasingly vital in modern telecommunications because they can carry vastly higher volumes of telephone calls, internet data, computer signals, much, much more than traditional electrical wires. And with very little signal loss, mostly just at the ends or from a bit of absorption. It's truly amazing what light can do when it refuses to leave its little glass tunnel.
Okay, let's shift gears a bit. From guiding light to light playing tricks on our eyes. Have you ever been driving on a really hot summer day and seen what looks exactly like a shimmering puddle of water way up ahead on the road, and then as you get closer, poof, just it vanishes?
Oh yeah, classic mirage. That's a perfect example of atmospheric refraction at work. This occurs because light bends as it moves through layers of air that have continuously changing densities, and therefore continuously changing indices of refraction. It's not a sharp boundary like water to air, but a gradual change. For instance, you can sometimes see the sun for a few moments, even after it has technically dipped below the horizon.
Really?
Because its light rays bend as they enter Earth's denser atmosphere, kind of carving around the planet just enough to reach your eye.
Huh. Okay, and the most common and sometimes frustrating visual trick from this is indeed a mirage. We often see these phenomena produced by refraction in the atmosphere, especially over hot ground like in deserts or, like you said, heated roadways.
Exactly, and what's fascinating here is the precise mechanics of how mirages work. Figure 1514 illustrates it pretty well. Hot air near the ground is less dense, right? And it has a different refractive index than the cooler, denser air higher up. So light rays from a distant object could be a tree, could even be just the blue sky. They travel through these layers. And as they hit that boundary zone between hot and cooler air, they bend.
Okay, so if I'm looking at, say, a distant tree, one set of rays comes straight to my eye the normal way, but another set travels down along a curved path, bending towards the hot ground, and then bending sharply back up towards my eye.
That's exactly it. And our brains, which are usually accustomed to light traveling in nice straight lines, they trace those bent rays back in a straight line from where they entered the eye, and doing that creates an inverted image below the real object.
Ah, and because our past experience tells us that inverted images on the ground usually mean reflections, like in water.
Precisely. Our brains, cleverly but incorrectly, interpret this as a shimmering pool of water reflecting the object or the sky. It's a really, really convincing illusion.
Okay, this next topic, I think, explains something truly beautiful, something that literally paints our skies. Let's dive into dispersion.
Dispersion, yes. Basically, dispersion is the process of separating polychromatic light.
Polychromatic, meaning?
Meaning light made up of many colors mixed together, like the white light from the sun. Dispersion separates that mix into its individual component wavelengths or colors. What's remarkable here, the key point, is that the index of refraction of a material actually depends on the wavelength of light. It's not quite the same for all colors.
Oh, interesting.
Yeah, so different colors having different wavelengths bend at slightly different angles when they enter a refracting material like glass or water.
Okay, that makes sense. So like blue light, which has a shorter wavelength, bends more than red light with its longer wavelength when they both pass into, say, a prism.
Exactly right. Blue bends more, red bends less. And this is perfectly demonstrated when white light strikes a prism. You can see this in figure 1515. Because of dispersion, the blue component is bent more significantly than the red. The light then fans out, separating into that familiar, stunning, visible spectrum, the colors of the rainbow.
Red, orange, yellow, green, blue, violet.
Ah,
ROYGBI.
that's the one.
Which of course brings us to nature's grandest display of this principle, rainbows. They truly are the most vivid natural example of dispersion. But how does one tiny little raindrop manage to create such a spectacular arc of color across the sky?
It's pretty amazing when you think about it. If we zoom in on what's happening inside a single raindrop, like in figure 1516b, it's like a miniature light show. Sunlight hits the water drop. First, it's refracted, it bends as it enters, and because of dispersion, the violet light bends the most, red light the least. Then, that separated light hits the back internal surface of the drop, and guess what happens there?
Uh-oh. Total internal reflection.
You got it. It's totally internally reflected off the back surface. Then finally, it refracts again as it leaves the front of the drop, spreading the colors out even more.
Wow. Okay, and this is why we see a full spectrum, like in figure 1516a, because all the drops are doing this.
Well, yes, but it's about the angles too. Those rays leave the drop at very specific angles relative to the incoming sunlight. Violet comes out around 40 degrees and red around 42 degrees. So when you look up at a rain shower with the sun behind you, you see different colors from different drops. It depends on the precise angle between the sun, the drop, and your eye.
Ah, okay. So a drop higher up in the sky might send red light down to my eye,
Right.
while a lower drop sends violet light,
Yep.
and all the drops in between fill in the other colors.
Exactly. They combine to form that breathtaking arc we see, and here's a fantastic little fact.
Hmm.
While we usually see rainbows as arcs above the horizon, if you happen to be at a really high vantage point,
Yeah.
like in an airplane or maybe looking down from a canyon rim,
Yeah.
you might even see a complete circular rainbow.
No way. A
Yeah.
full circle. That must be incredible. I'd love to see that. Now, we often kind of assume that lenses, in our cameras or eyeglasses are perfect. But they're not always, are they? These very principles we've been discussing actually help explain why lenses aren't quite perfect.
That's a really important point. It raises questions about how our optical instruments actually work. We generally draw diagrams like light rays focus perfectly at a single point, right?
Yeah.
But that's an idealization. It's not always true in the real world. One common issue is called spherical aberration. This basically happens because light rays passing through the outer edges of a spherical lens don't focus at quite the same spot as rays passing through the center.
Okay.
Result: you get a slightly blurry image. It's especially noticeable in simpler lenses or when the lens opening, the aperture, is wide.
And there's another type of lens, imperfection, right? Chromatic aberration. That sounds like it ties directly into what we just discussed with dispersion. How does that one work?
Exactly. It's directly related to dispersion. Chromatic aberration is the focusing of different colors of light at slightly different distances behind a lens. Since the index of refraction varies with wavelength, remember, different colors bend differently. Violet light is refracted, or bent, more than red light by a simple lens.
So they don't focus at the same point.
Nope, they focus at different points. Figure 1517 shows this pretty clearly. This can lead to those noticeable color fringes, sometimes like purple or green halos around objects in a photograph, especially around high contrast edges.
So it's not just some, abstract problem for physicists. It's literally why a high-end camera lens might cost a small fortune.
Mm-hmm.
And why your smartphone camera has to use really complex software to correct for these subtle flaws automatically.
That's right. Understanding these principles allows engineers to design better optical systems, sometimes using multiple lens elements made of different types of glass, to actually counteract these aberrations and give us clearer vision, moving beyond the inherent imperfections of light itself.
Yeah, it's amazing how they can correct for that.
Well, today we've gone on quite the journey through light. We started with total internal reflection, saw how light can be trapped and guided, leading to incredible technologies like fiber optics that, basically power our connected world. Then we explored how atmospheric refraction plays visual tricks on us with mirages and makes the sun linger a bit after sunset. And finally, we uncovered the magic of dispersion, explaining why prisms split light and how rainbows paint the sky. We even touched on how these effects influence the very design of the lenses we look through every day.
So thinking about all this, what stands out to you, the listener, about how light interacts with the world? I mean, from the invisible dance of light giving a diamond its unparalleled sparkle, to the internet data zipping through hair-thin fiber optic cables, and just the ephemeral beauty of a rainbow. These seemingly complex physics concepts are truly at play all around us, constantly influencing both the natural world and our most cutting-edge technology. It's worth considering how understanding these fundamental behaviors of light doesn't just help us appreciate phenomena we often take for granted, but it also empowers us as humans to design and engineer systems that literally illuminate our world in ways that were once unimaginable. How might knowing this inspire you to look at everyday objects or just events like a sunset or a rainy day with a new sense of wonder? Maybe asking yourself, how is light actually doing that?